Alright, let's start, guys. I have to figure out a way to bring more people to class. I can either offer incentives like raffles, chocolates, or get nasty and give quizzes and things like that. So, I mean, this is not intended. You are obviously here, right? So those of you who are watching now, beware. Yeah, I'll just turn it off. Exactly. I'll turn off the mic and solve a few midterm problems, you know. That will help. Okay, so we'll talk about Fourier series today, but in discrete time. So we're switching from continuous to discrete. So in many ways, discrete time Fourier series is actually easier. Okay, but we have to, you know, there's some indexing and things like that that make it not the writing a little messier, but actually conceptually it's a lot easier. So before we delve into this, a few words about discrete time periodic signals, and nothing is fundamentally different here, of course. So X is periodic with period N. And of course now N has to be an integer, so that's a key difference from continuous time. In continuous time, T can be anything, right? But now, because we're in discrete time, it has to be an integer. So, is that the sign for integers? So let's just say, put this positive, so positive integers. With period N, if x of little n plus n is equal to x of little n, no matter where I start, for all n. Okay? So, like in continuous time, you know, multiples, integer multiples of n are also periods. So we should call the smallest such n, the smallest such integer, the fundamental period. Okay? So a question. So is x of n cosine omega 0 n, omega 0 is some frequency, okay, periodic for any omega 0. What do you think? My questions are usually trick questions. So whatever you think the answer is, say the opposite so you can impress people. So what do you think? So let me rephrase the question. Is cosine of n periodic? Remember, n is 1, 2, 3, 4. Does it ever go back where it started? No, right? It never, little n will never be an integer multiple of 2 pi. It just doesn't happen. Because n is an integer, 2 pi is not rational, pi is not rational, right? So the answer for this signal is no. So what would be a general answer? When could I say yes? Anyone? Yes? You need some pi in there, right? You need a pi in there so that, you know, some integer at some integer value of little n, you get an integer multiple of 2 pi, right? So basically what we want is this, right? For this to be periodic, we need, what we need is that omega 0 times n is our candidate for a period, right? That needs to be 2 pi or an integer multiple of 2 pi, right? If you can get away with, you know, making this equal to 2 pi with an integer n, you're done. But that may not be possible. In general, you may have to settle with an integer multiple of 2 pi. So let's call it m, okay? So the answer to the question is yes, if there exists this sign, remember, is that there exists integers n and m such that this is true. Okay? And the smallest n that will make that true will be your fundamental period. Okay? So for cosine, the first question was, what if we are looking at cosine n, in which case omega 0 is 1, right? If omega 0 is 1, the left-hand side is always an integer. The right-hand side is always an irrational, okay, which will never be an integer, no matter what I multiply it with, right? So that's why cosine of n was not periodic, okay? But let's look at other examples, such as cosine pi by 5 times n. That is periodic. Omega 0 in this case is pi by 5. Can I find an n such that this is equal to 2 pi? Of course, if n equals 10, right? So that's my period in this case. Let's look at cosine 5 pi by 7 n. That's also periodic. Can I find an n such that 5 pi by 7 times n is 2 pi? Is there such an n? Integer n? Integer n? If I could take 7, but that's, no, I mean, there is none, right? So that would 14 by 5, that's not an integer. So I do now need to introduce an m here. So what is the littlest n and m you can think of? N is 14 and m is 5. Okay? So that example explains why in general we need an m. We can't expect to hit exactly 2 pi. It may have to be an integer multiple of 2 pi. Okay? Alright, so we found two. So basically the answer to the question is, yes, it's periodic if you see a pi in there. Okay? Without the pi, you're doomed. Right? So if I add these guys up, what do I get then? 5 cosine pi over 5n plus cosine 5 pi by 7n, also periodic. I've added two things here. Both are periodic. The first has period 10, the other has period 14. So the period, the fundamental period for the sum would be the 70, which is lowest common multiple. That's the first time they will meet, of 10 and 14. And that happens at 70. All right? Okay. One more question before we move on. Is the sum of two discrete time periodic signals periodic? I asked you this question in continuous time. Back then it was a trick question because the answer was not necessarily. I could have cosine t plus cosine pi t, where the two never met, right? But now think about it. I said, is the sum of two periodic discrete signals periodic? So when I qualified by saying sum of two periodic discrete signals, I already front-loaded the question of this rationalness business, right? So this pi is by assumption in both of the signals, right? So then, they both have their, periods n1 and n2. It just amounts to finding the least common multiple of n1 and n2, right? So unlike in continuous time, in discrete time, sum of two periodic signals is periodic. And the common period is the least common multiple of the two numbers, which are integers. Those being integers, basically makes that possible to say yes in discrete time, right? Okay? In contrast, in continuous time, I didn't have this. If I could tell you, cosine t, cosine anything t, right? That's periodic no matter what. There I didn't have to have this condition. So this condition here at the top, the one in orange, front loads the issue that we saw in continuous time that made the sum not necessarily periodic. So that is gone by definition of periodicity in discrete time. Therefore, when you add two discrete time periodic signals, it's automatically periodic. All right? Good? All right. While I'm asking you questions, let me ask you one more. So here's the question. So which one oscillates faster? Cosine, it could have been sine. Cosine pi n or cosine pi of 3 pi over 2 n. So here omega 0 is pi, here omega 0 is 3 pi over 2. I've increased omega 0, right? But which one oscillates faster? What does cosine pi n look like? This one, the first one. At n equal to 0, it's 1. At n equal to 1, it's negative 1, positive 1, negative 1, and so on, right? What does this look like? At n equal to 0, you are at 1. At n equal to 1, what are you? 0. At n equal to 2, you are at cosine 3 pi, which is the same as cosine of pi, which is negative 1, right? And 3, no, wait, yeah, that's n equal to, and 3, 9 pi by 2, cosine of that is again 0. So I oscillate like that, right? I do oscillate for sure, they are both periodic. But in the first case, the period is 2, in the other case, the period is 4, right? So even though I increased omega 0 here, this is a bigger omega 0 than this, right? I'm now oscillating slower. How is that possible? There is no such thing in continuous time, right? If I give you cosine omega t, if you increase omega, it's going to oscillate faster and faster. There is no limit to how fast you can get, right? But remember the phrase you should say to yourself every night before sleep. Pi is the highest frequency in discrete time. The moment you go past pi, you're actually oscillating slower. Okay? So I have a pretty picture in the notes to visually convince you of that. And this is basically a hacked version of the plot that I showed you earlier, where what is this? No, we're not talking about mode consistency, not that. Where is it? Yeah, here. Yeah, so this is my pretty picture for why pi is the highest frequency. So remember, I had this other pretty picture, which is where this came from after a little bit of editing, where we looked at points in the complex plane and plotted e to the j, that number, complex number raised to power n. So now I'm looking only at points on the unit circle so that the amplitude of oscillations do not grow or decay. So amplitude is sustained, right? And I'm looking at different angles, right? Omega equal to 0 is basically a constant, right? As I increase omega to pi, the oscillations will get faster. They will oscillate more frequently, right? And at pi, which is the left end, you hit the max. The moment you go past pi, you start getting slower again. In fact, pi over 2 and 3 pi over 2 are basically oscillations with the same frequency, right? And then when you come back to 2 pi, you're actually, again, not moving. Okay? So there's that kind of periodicity in omega. So in discrete time, if I give you cosine omega 1t, cosine omega 2t, tell you omega 1 is bigger than omega 2, that means nothing, right? You just have to compare them relative to pi. Okay, so in addition to saying this to yourself before sleep, take a look at this picture before sleep. Yes? So wait, what do you mean? We're in discrete time now. So what are you saying? Cosine? Okay. But don't say hertz. Hertz is in continuous time. We're in discrete time now. So the question is remember, n is an integer. N is 1, 2, 3, right? So what's the period of the signal? What does the signal look like? N 0, you have 1. N equal to 1, you have cosine 40 pi, which is already a multiple of 2 pi, right? So you're not going anywhere, right? Your period is 1 or 0, whatever you want to call it. It's a constant signal. So I think you're thinking continuous time when you say hertz. And remember, in discrete time, we're dealing with integers, and that creates some peculiarities in the signals. All right. Let's talk over the break, okay? So formulate your question. Are you stretching or do you have a question? Okay. All right. All right. Okay, so those are the basic questions we want to talk about. Now we can actually talk about Fourier series. Very similar to continuous time, really. I mean, there is hardly any difference. A few little differences. For the better, I would say, just simpler. Fourier series. So, the idea again is the same. Express a period n sequence, now because we're in discrete time, sequence x as a linear combination of what we might call basis sequences. In continuous time, these were e to the j k times the fundamental frequency times t. Now it's going to be the same thing, e to the j k again. The fundamental frequency now is 2 pi by n times little n, which stands for the time instant, right? So k is the index of the function. Each k gives us a different function, right? So we're going to call these phi sub k of n. All right? So just it's good to have a name. Not essential, but helps reduce notation. So we're going to call them phi. Does anybody have an issue with the letter phi? You're all good with it? Okay. All right. So it's not one of these confusing Greek letters like upsilon, or there are weird ones that is xi and zeta. Anyway, so phi is easy. Okay, so these are the functions. So basically the idea then in Fourier series is to write the sequence x as a weighted sum of these guys. All right? Same as continuous time. In the continuous time we had the identical thing. Big N was big T, little n was small t. All right? Same idea. Now there is a big difference though. Okay? In continuous time, every k is its own function. If I increase k, I'm a faster oscillating signal, right? But in discrete time, there's a limit to how fast you can oscillate, right? So it turns out you can't claim anymore, because of the integer nature of little n, that each k is different from each other. They actually start repeating themselves. So in particular, if I look at phi of k plus n of little n, I can apply the same definition, k plus n. So I've just advanced the index by capital N, right? 2 pi over n times n. But then I can split this as e to the j k 2 pi over n times e to the j n 2 pi over n n. So these n's cancel, and little n is an integer. So what you're seeing here is e to the j, 2 pi, 4 pi, 6 pi. They're all the same things. They're all 1. Right? So this is really 1. And this is what we started with. This is phi k of n, right? So you come back to phi k of n if you advance the index by capital N. So these functions are actually periodic themselves in their index k. Okay, so if the period is, say, 6, phi sub 0 is the same as phi sub 6, same as phi sub 12, 5 sub 1 is the same as 5 sub 7, and all that stuff, right? So therefore, unlike the continuous time Fourier series where we had an infinite sum running from k negative infinity to k positive infinity, in discrete time there is no point in doing that. These functions, these sequences phi, there are only finitely many of them. How many different ones? We'll see shortly that they are different, but we do at least know that we don't need more than n because they start repeating themselves, right? So we'll use that property and define the Fourier series in a slightly different way. So we're going to say, so the Fourier series is going to look like x of n equals sum no longer from k negative infinity to positive infinity, but rather from, say, k0 to n minus 1, or from k equal to 1 to n, capital N, right? ak phi k of n. All right? I can, I just have to choose, because of the periodicity in k, I just have to choose k to be successive integers, right? Say from 0 to n minus 1, or 1 to n. So what we will say instead, because the choice is really yours, whether you want to go start from at 0 and at n minus 1, or you want to start at 1 and at n, or you want to start at 2 and at n plus 1, it's all your choice. So to allow all choices, we're going to use this notation here, where these brackets will mean any any n successive integers. Your call where you start. Integers. Okay? So that's the Fourier series. Biggest difference is that it's a finite sum. That's actually a good thing, right? Finite sum means we don't have to deal with all the convergence issues. Remember the Gibbs phenomenon, all that stuff, weird oscillations. There's none of that here. You add n terms, you exactly recover the sequence you started with. That's it. No convergence problems. Any questions? Okay? Yes. Function, different, multiples of the fundamental frequency 2 pi by n. Okay? Let's look at an example. Here's a simple picture. So let's take the period of our signal for which we are doing the Fourier series expansion as 6. That means 6 of these phi k's, perhaps starting at 1, ending at 6, is enough, right? So let's look at these functions phi, these sequences phi sub k, right? They are complex valued by their very definition. So here's my other pretty picture. It's here. It's not that pretty, this one. Okay. So for n equals 6, phi sub k of n is e to the jk 2 pi by 6, which is the fundamental frequency omega 0, right? Times little n, which stands for time, right? Each k is different from each other until I start repeating, until I pass 6. K1, K2, K3, K4, they are different, but K6 is the same as K0. K7 is the same as K1. So let's look at k equal to 1. What does this function say? It says e to the j 2 pi by 6, which is what? 60 degrees, right? Times n. So it's complex valued. We know it has magnitude. The complex number has distance 1 from the origin in the complex plane. Its angle, its phase, is 60 degrees when n is equal to 1. when n is equal to 2, it's 120. So let me just show it here. So this is for n equal 1. For n equal to 2, you tick twice, right? For n equal to 3, you're here, and so on and so forth. So at every time instant, this complex number in this sequence for k equal to 1 is flipping by 60 degrees in the counterclockwise direction. Naturally, it's periodic with period 6 because of the way we defined it. And at time equal to 6, it comes back to where it started, which is positive 1. Right? So that's k equal to 1. K equal to 2 doubles the frequency. So what that means is that now I substitute k equal to 2. So instead of advancing by 60 degrees each time, I'm going to advance by 120 degrees each time. Right? So phi sub 2, therefore, is this function here as a function of time. At time equal to 0, again, angle is 0, so we have a real number 1. At time equal to 1, we flip by 120 degrees. So it's a complex number. Time equal to 2, it becomes 240. Time equal to 3, back to where it started. And of course, since it's periodic with period 3, it's also periodic with period 6. Okay? So are you convinced these are two distinct functions? Okay? K equal to 3. Now, I'm multiplying the angle 60 by 3, 180. So that means that every time I'm going to rotate by 180 degrees. That means this sequence, this particular sequence is a real valued one. It starts at 1, goes to negative 1, comes back to 1, and so on. Right? It has period 2, therefore also period 6. So you can do this for all k's up to 6. And at 6, something funny happens. So by how many degrees am I advancing each time? K is 6, so I'm just, k times 2 pi by 6 is 2 pi. So at each time, I'm going to rotate 360 degrees. That means I'm not really rotating, right? I'm just staying where I am, right? That's why this particular function, phi sub 6, is the same as phi sub 0. If I were to take k equal to 0 here, right, I would get a flat 1, e to the j0, which is always 1, no matter what little n is. And so I would get a constant signal like this. All right, so this picture summarizes a lot of things, right? So if I were to take k equal to 8, it would have looked the same. If I were to take k equal to 0 or 12, it would have looked the same. If I were to take k equal to 7, it would have looked the same as this, right? So that's the periodicity of these functions. They are not only periodic in the time argument little n, they're also periodic in their indices k. Therefore, we only need n of them. In this example, 6 of them will be enough. All right? So that means, Fourier series in this case means any period 6 signal, I can represent it as a weighted sum of these 6 complex valued functions. If the signal that I'm trying to represent is real valued, the coefficients of these functions will be such that the imaginary parts cancel out, so I end up with the real valued signal that I started out with. All right? So a few properties of these 5 functions that we use in the Fourier series, which are obvious, and the picture right above that sort of illustrates why. First of all, these functions are periodic in n, with period capital N. That's obvious from the way they were constructed. So let me write it anyway. Phi sub k was e to the j k 2 pi over n times little n. If I change its argument to n plus n, I'm going to get e to the j k 2 pi by n times little n plus big N. And that separates as e to the j k 2 pi over n times e to the j k 2 pi, because the big n's will cancel and this is equal to 1, right? So by construction, these guys are periodic, so that's the easiest property. The second property we already observed is that These are also periodic in the index k. So I don't need 7, 8 functions if n is equal to 6. I just need 6 of them. So if I advance the index by n, I recover the same exact function. The third property says that these functions phi sub k, almost always have an average of 0. Look at the one on the left top, right? If I add those 6 arrows, what do I get? They sum to 0, right? You see the same phenomenon for almost all k with one exception. K equal to 6 or k equal to 0. In general, k equal to capital N. Those are the exceptions. Because when I'm averaging over one period, phi k of n, right? If k is 0 or n, capital N or capital 2n, 3n, etc., then I'm really adding ones, right? Just like in this picture here at the bottom right. Okay? So then this sum will give me n. If, however, k is not an integer multiple of capital N, those arrows you see in the picture will cancel each other out. They will add up to 0, and therefore the average will be 0. Okay? So a convenient way to write this is when, I'm going to write this here, when k, instead of writing it this way, which is nasty, we can just say when k is equal to 0, modulo n, in our example that includes k equals 0, k equals 6, k equals 12, etc., then the average is capital N, different than 0, otherwise it cancels out. Is that clear? Yes. Okay, sum. Yeah, I should have said average is 1 maybe, but sum. Okay, sorry. Any other questions? All right, the last property is very straightforward. If I multiply two of these sequences, phi k and phi m, I'm simply multiplying e to the j k 2 pi over n times n and e to the j m 2 pi over n times n, and therefore I can add k and m, and that means I recover another phi function whose index is k plus m. And of course, if k plus m goes beyond capital N, you just can do the modulo of that. Right? I'm not going to do that because, we already understand that phi 7 means the same thing as phi 1, so we don't need to make provisions for modulo every time. Right? Good? No questions? But they are, because by definition. All right. Okay, so, all right, let's go back then. So I think we all believe the Fourier series now. It's finite, pretty, and all that. The next question is, like we did in continuous time, how do you find the coefficients? How to find A sub k. Okay? This derivation is actually very simple and similar to continuous time. We go backwards. We start with the series. We say x of n is the summation over k for n successive integers of a sub k phi k of n, right? So I need to be able to single out these coefficients. In this expression, there are n of these a's, right? I want to find a way to get rid of n minus one of them, so only one of them remains alive. Okay? How do I do that? The idea is simple. Multiply let me rewrite it. to find a sub m, a particular value of a, multiply both sides of this expression with phi negative m of n and sum over one period. Okay, so what does that result in? So you take x of n, multiply it with phi minus m of n, and the right hand side becomes again the sum a sub k phi k of n times phi negative m of n. Right? But then the last property we saw said that if I multiply two of these 5 functions, it's the same as adding their indices. That was property 4 in what I just showed you. So this is the same as phi k minus m n. Alright? Okay, so that's the first thing we do. And then I said multiply both sides with phi negative m, which we did. And now let's sum both sides over n. So we're taking the sum over one period of time of xn phi of negative m n. And on the right hand side, this will give me a double summation of ak. So we're summing over both n and k of ak phi k minus m n. Okay? When you have double summation, just like double integration, you can change the order of those, right? Nobody's going to care. So let's change the order. So that means first sum over n instead of k, and then sum over k. All right? Okay, so but then when I change the order of the summation, something good happens. The inner summation is running over time little n, and it could care less about what a sub k is. K is independent of n. So what I can do, because I changed the order, is that I can take a k out of the inner summation. So I can express this as sum over k, a sub k, sum over little n, phi k minus m n. Right? Now, you tell me, someone, what is this equal? I said average, but you corrected me as sum because I wasn't dividing by n. That's fine. So what is that sum going to give me? Almost always 0, right? Like in our pictures where the arrows were pointing in opposite directions, except when the index is 0 or any integer multiple of capital N. Alright? So that means this is either N or 0, more often 0 than N, right? 0, capital N, only when k minus m is 0 in modulo n, which is the same as saying k is m k is m modulo n, right? And 0 otherwise. Say it again, I'm sorry. Yeah, absolutely. Right, yeah, exactly. But yeah, in general, if you haven't done that, then you put that modulo n. Okay, so now if you step back and look at the outer sum, we're adding ak times something over k, but that something is almost always 0, so you're not really adding anything except for one term that is non-zero. The term the k for which what I'm adding is not 0 is k equal to m. That's when this is non-zero. Okay? So even though it appears that I have a sum on the right hand side, it really is not a sum because I'm adding zeros and only one non-zero term, which is n. And that happens when k is equal to m, so I get n times am. The left hand side is still a sum over time, xn by negative m of n. And that gives me, that's the answer I was looking for. If I'm looking for the coefficient a sub m, the way to find it is divide this by n, this n goes away, you just have to do this sum, divide by n, that will give you a sub m. Right? This equation is sometimes called the analysis equation. So that's because we are taking a sequence x and analyzing it. We are finding its Fourier series coefficient. That's some kind of analysis. And the Fourier series representation itself that was here is called the synthesis equation. And that's because we are synthesizing x from these frequency components. We are adding them up with appropriate coefficients to recover x. Okay? So somebody called those equations synthesis and analysis equations, and they stuck. So don't blame me for it. Okay? So that's it. So if you want to find the mth coefficient, you just have to add capital N numbers, complex numbers, average them. That's it. You found your coefficient. Did you have a question? Yes. Yes, there is, and I'll ask you to wait until maybe another half hour. We'll see. We'll talk about that. Okay, other questions? Yes, we'll do an example. Yes. Patient, guys, we can't wait. Okay, here's an example. Well, actually, before the example, one property. All right. So this is very similar to what we observed in continuous time. If we have a real valued signal x of n star for all n, right? So that means the Fourier series of this, which is a sub k by k of n, must match the Fourier series of that, which is the same thing but with a k star and phi k star. Now remember, phi k is e to the j k 2 pi over n times n, right? So starring that amounts to putting a negative sign here, and that amounts to replacing k by negative k, right? So phi k star is phi of negative k. All right, so this is phi of negative k of n. All right, so, and let's switch from a k representation to an m. Let's call negative k m. So then, instead of counting over k, I can count over m, and I can write a negative m star by m of n, right? So there you go. On the left here, you have the Fourier series of x. On the right, you have the Fourier series of x star. And if x is a real signal to begin with, those Fourier series have to be identical. That means the coefficients themselves have to match, right? So if I go back to k here, call this k again, call this k again, right? That simply means ak is a negative k star. That's something we saw in continuous time Fourier series. If I looked at A1 and a negative 1, they were complex conjugates. If I looked at A2 and a negative 2, they were complex conjugates, right? So the same thing happens here as well. But in discrete time, I have a further property that I did not have in continuous time. These coefficients are also periodic because the phi k functions themselves are periodic. So now I have the property that advancing the index k by n changes nothing. I get a k, right? Okay? So what that implies is, if I advance both of them by n, add n to the index, that won't change the values, right? So then that means a k plus n is a wait, what am I talking about? Oh, wait. So I'm sorry. Okay, so not both, of course. If we just advance this guy, add n to this, nothing will change because of this periodicity. So a n minus k star is the same as a k star. That's because of the periodicity of the coefficients that didn't exist in continuous time. So that means if n is equal to 10, a1 and a9 are closely related. They are complex conjugates. a2 and a8 are complex conjugates. a3 and a7 are complex conjugates. So if the indices add up to 10, they have to be complex conjugates of each other. Okay? So we'll see this in an example now. Example. This is an example where I'm not going to have to do the analysis equation because this example comes in the form of sines and cosines already, which we know how to split into complex exponents, so we don't have to do that sum in the analysis equation to find the coefficients. This is just given as sine 2 pi by 10n cosine. I have no recollection where that example came from, why these numbers, but anyway, it doesn't matter. It's a contrived example as always. Pi by 4, and that's it. So what's the period? The sine has period 10. The cosine term has period, fundamental period equal to 5 is enough, right? You hit 2 pi already at 5. So the first has 10, the other has 5. The least common multiple is 10. So we're going to take n equals 10 as our period. That means we're going to define phi k as e to the j 2 pi over 10. Well, let me put k first because that's how I was writing it before. K 2 pi over 10 times the length. Alright? Something is slightly bothering me with my notation here. I call it phi k of n, right? In reality, it also depends on the period 10, right? But, it's very inconvenient to have to index phi with another n, so that would make a mess of indices. So when we talk about phi k, implicit in that notation is that there is a given period n, and that n factors into the definition of phi k, in this case in the form of division by 10 here, right? Okay, so, well, I don't need to do the synthesis analysis equation. In fact, that would lead to messy expressions. Simply remember that I can write this as 1 over 2j, e to the j, 2 pi over 10n, negative 1 over 2j, e to the negative j, 2 pi over 10n. Similarly, this is 1/2 e to the j, 4 pi over 10n, plus 1/2 e to the negative j, 4 pi over 10n. Now, which phi is this guy? Which k? k is 1. So this is our phi 1. This is phi negative 1. But if we choose to go over k, say, I don't know, what did I do in this example? Let's go from 0 to 9. It could have been 1 to 10, doesn't matter. But if we choose this, 0 to 9, then phi negative 1 is not a valid k. But that's the same as phi 10 minus 1, which is 9, right? So this guy here is phi 2, right? This is phi negative 2, but that happens to be the same as phi sub 8. Okay? And we don't have other terms. This guy, we have one more term. Which phi is this? This is phi 0. If I had gone with k1 to 10, I would have had to write it as phi 10. Right? Okay, so that means I already have 5 terms here, right? In general, for a period 10 signal, I would need as many as 10 terms, but in this case, I got away with only 5 non-zero terms. A0, the coefficient of phi 0 is 1. What did I do wrong? Any complaints? Of course I'm missing the face. Thank you. So the face has to go here in the form of e to the j pi over 4, right? Yes. And then here, thank you for catching that. E to the negative j pi over 4. Yes, thank you. So A0 is 1. The coefficient for phi 1 is 1 over 2j. The coefficient for phi 2 is 1/2 times e to the j pi over 4. What is that anyway? 1 over square root of pi over 4 is what? 45. So it's like 1 over square root of 2 plus j times 1 over square root of 2. If you want to write it that way, you can, but I'm not going to bother. What is A3? There's no such thing. Phi 3 did not make an appearance. There was no A4 either. No 5. Alright. No 6. In fact, because A4 is 0, I can already say A6 is 0 because they need to be complex conjugates, right? Likewise, A3 is 0, so A7 has to be 0 because they are complex conjugates. When the indices add up to 10, they'll be complex conjugates, right? Anyway, so the A0, A1 are here. 3, 4, 5, 6, 7 are 0. A8 is the coefficient here, which is 1/2 e to the negative j pi over 4. How does it compare to A2? Of course, it's the complex conjugate. And A9, I'm not even going to write it, it's going to be A1 complex conjugate. That is negative 1 over 2j. Alright? So that kind of shows the conjugate symmetry property for the real valued x, as well as the periodicity of these coefficients in your index k. If you do not have any questions, we'll take a 5-minute break and continue after. start again. Okay, so that was our first example where we didn't have to move a finger. I mean, we had to do calculations, but we didn't have to do the analysis equation. Here's an example where that analysis equation is necessary because I don't have sines and cosines that I can readily decompose, right? So we're looking at a rectangular pulse train. We had a similar example in continuous time, so this kind of mirrors that. We had a pulse train there too. So capital N is not specified, it's the period, and N1 is where this ends. Okay, fairly general. The special case where N1 is equal to 0 gives us a signal that looks like what? N1 0 means this guy is not there, this guy is not there, neither is this, neither is this, so those just disappear. So I have an impulse that appears every n samples. Right? So it's a periodic impulse. So that is called an impulse train. We'll see that word a lot. It's a train of impulses, so to speak. So that becomes sort of a special case of this general signal, pulse train. So let's do the easy case where n1 is equal to 0. If I apply the analysis equation, a sub k comes from 1 over n, sum over one period of time. It's up to you how you select that, where you start and where you stop, times x of n phi negative k of n, which is the same as e to the negative j k 2 pi over n times little n. Okay? But because of the way we constructed, we selected n1 equal to 0, right? This summation here, let's say we sum from 0 to n minus 1, that is going to be not really a sum, right? If I start at time 0, start here, stop counting here, everything on the way is 0 except for little n equal to 0. I only have to account for this. There's nothing else to add, right? So then I don't need to sum. I just need to look at this, what I'm summing at n equal to 0, and this will give me 1 over n, x of 0, and because little n is set to 0, this term also becomes 1, and that's it. And what is x0? It's 1. So 1 over n. Strangely, what I found did not even depend on k. Right? So I have n Fourier series coefficients here, perhaps a0 to a n minus 1, if that's how I'm doing the counting. And they're all equal. They're all equal to 1 over n. That's a peculiar thing about the impulse train. All right? Yes. And one is basically the width, the duration, right? So if we set n1 equal to, it's where this guy ends, right? If we set n1 equal to 0, basically we have one impulse, nothing else. And it comes back at time n. So it's periodic. Okay, so that's the interesting thing. So that means for an impulse train, all Fourier coefficients are the same. They're all equal to 1 over n. That seldom ever happens. In fact, the moment I change n1 from 0 to anything else, I lose that property. I have to do a lot of messy calculations. So let me just do that for n1 equals 1, and then I'll show you the general result. Not that, sorry. So let's take n1 equals 1. So then the signal looks like this. 1, 1. So n1 equals 1. At n again, these guys make an appearance. Alright? And let's decide now that we are going to add from 0 till n minus 1. Well, why am I doing that? Let's start from, okay, let's do it this way. Let's start from negative 1, 0, 1, and let's stop before the next one arises here, right? And minus 2, okay? Because that will be the symmetry will help, because this will be matched, this term will be matched by this, right? So they're all 1s. So this is our x. So I'm trying to find a sub k, and the expression is 1 over n. Now I decided to sum from negative 1 to n minus 2, but really I have nothing to sum after n equals n1, which is 1, right? X of n, which also is 1 in this interval, times e to the negative jk 2 pi by n times little n. Alright? So there really are 3 terms being added here. N equal to negative 1, n equal to 0, and n equal to 1. Yeah, negative 1. Thanks. Okay, so, let's do it. So for negative 1, I have e to the j k 2 pi over n. For n equal to 0, this is for n negative 1. N equal to 0, I have simply 1. N equal to 2 positive 1. I have e to the negative j k 2 pi over n. Alright, so you know how to combine these things, right? What do I get? Cosine, 2 times cosine, right? Because if I divided these two, added by 2, that's dividing a cosine. So 2 cosine 2 pi over n k. And there you go. This is an expression for your a sub k. Okay? So this is for n1 equals 1, right? And so if I were to, so what does that look like? Let's say the period is 10. What do these coefficients look like? When k is equal to 0, I have 1 plus 2. So I start at 3. So this is my a0. Now the indices are k. a1 will be, so basically as k advances by n, if it goes from 0 to capital N, I'll come back to 3. But in the meantime, I can go as low as negative 1, right? In the middle. So basically this will have an envelope like this, and at k equal to 10, it will come back to where it started, but k equal to 10 is the same as k equal to 0, so we don't need to count that. So you gotta get things like this, right? So the Fourier series coefficients are going to be points on that cosine thing, right? So unlike the case where we had an impulse train and 1 equal to 0, in this case, not all a's are the same. They are actually changing. Okay? So if you are patient, you can do this type of calculation for any n1. In fact, it's done in the notes. Actually, it's not done in the notes. The note says do it. Okay, so if you do it, it says, for any n1 different than 0, this is what you're going to get. Okay? And presumably, this encompasses every expression we had so far. So if you set n1 equal to 1, what you see here should recover that cosine expression we had. All right? So, and what we are looking at the bottom here is the partial sum. I'm showing not the sum of all k's going from 0 to n minus 1, but going from negative m to m. So, and I think this figure is for, this figure is for n equal to 9. N equal to 9 and 1 equal to 2. All right, so these are the partial sums, adding only some of the 9 terms I need to fully recover the periodic signal. If I only use m equal to 1, that means I only take into account a1, a0, a negative 1. Only 3 terms out of 9 are used, right? And obviously I'm not going to recover the pulse train I had, right? That was a square-shaped thing. This doesn't look anything like that. But as I keep adding more terms, if I'm looking at m equal to 2, now that means I go from k equal to -2 to +2, so that I actually to 5 out of the 9 terms I need to reconstruct the full thing. So it's getting closer to a square wave. M equal to 3 means I have 7 terms. I started at k -3, went to +3. There are 7 terms. Getting very close, as you can see. And at m equal to 4, I have everything. M4 means I'm counting from k equal -4 to k +4. That gives me 9 terms, which are enough for a period 9 signal like this. Okay? I don't need anything else. That's the full Fourier series. 9 terms is it. Okay? And you perfectly recover the square wave that we started with. Right? No such thing as Gibbs or all those stuff that we had in continuous time, because continuous time Fourier series is an infinite sum. The moment I truncate somewhere, I have to deal with the consequences. Discrete time Fourier series are finite. You get away with capital N terms, and that's all you need. You fully recover the signal. All right? You're done. Okay, no convergence problems. No need for Herr-Dirichlet. Nothing like that. Okay? Any questions? No. All right. So that's pretty much it. So I have below here a summary of what we've seen so far. Continuous time and discrete time Fourier series. The synthesis equation in continuous time is a summation. Big difference from synthesis equation in discrete time on the right-hand side is that we have infinitely many k's. Each one is different. They are different functions. Each larger k is a higher, faster oscillating signal. In discrete time, we notice that these guys are not different. They keep repeating themselves. K plus n is the same as k. Right? That's why we now get away with a finite sum, and we don't have to deal with convergence problems of any sort. Analysis equations, that's how you calculate the Fourier series coefficients. In the case of continuous time, it's an integral over one period. It's your choice where you start. If you start at 0, you should stop at capital T. If you start at -t/2, you should stop at t/2. So you do that, and you get the coefficients. In discrete time, of course, in integration over time becomes a summation over time. Again, you do this for one period. Choose where you want to start. It's a periodic thing that you're adding. So as long as you add n successive terms, you're done. And divide that by n, and that will give you the Fourier series coefficients. So this is it. That's what we've been doing this week. And it's a quick summary of everything. Now, we talked about some properties in continuous time, and there are analogous properties in discrete time. Very few differences. I mean, there are a couple of differences that we already noticed, like the phi case being periodic and all that. And those little differences may result in slightly different properties. So if you have a copy of the book, you can look at tables, and I took pictures of those today. Table 3.1 for a list of the properties of the continuous time Fourier series. Some of these we talked about last time, such as linearity. If you have ax plus by, you just do the same thing to the Fourier series coefficients. If you have a time shift, the Fourier series coefficients get multiplied by an e to the -j term with an appropriate phase. There are some others we didn't talk about. The conjugate symmetry we talked about. If we look at x star of t, the Fourier series coefficients are starred, and the index becomes -k. And some consequences of that was that if we have real valued signals, a -k and a k were cousins. They were conjugates, right? And we also noticed that if you have a symmetric signal, even symmetric signal, that actually leads to real coefficients. That's the last thing we showed last time. And some other properties that we did not explicitly state, they could perhaps one day become homework problems, who knows. One interesting property is this. It's called Parseval, like the opera. Is it an opera, or I don't know what it is. All I know is it's loud. I can't stand it. So, Wagner. Wagner. So Parseval's relation says the following. You have your periodic signal x of t, and somehow you have the Fourier series coefficients. If I square x of t and integrate over one period and divide by t, so this is like the root mean square of x, that is going to be the same as the Fourier series coefficients squared and added from k negative infinity to infinity. Right? I mean, obviously, these Fourier series coefficients are an alternative representation of a periodic signal, so that kind of makes sense that there is a relation between those. But why that particular relation? That may not be very obvious. It's not hard to derive. But for now, take it as a fact. Some guy proved it, right? But we'll see shortly that this is actually a very nice geometric interpretation for that, right? So, okay, so that was the continuous time properties. Discrete time is another table, table 3.2. Some things that didn't exist before, such as the coefficients being periodic, phi's being periodic. Linearity is the same. Time shift is very similar. If you're shifting the signal in time, the Fourier series coefficients are almost the same, except that you add phase to them. You just multiply them by e to the negative j something, where that something depends on how much you shifted in time. Conjugate symmetry, all that are similar, and other things. And there you go, again, Parseval comes. So, in this case, we have a discrete signal, x of n. So, x of n squared sum over one period and divided by the period is the same as the Fourier series coefficient squared and sum over n of those coefficients and successive values of those coefficients. Okay, again, we'll talk about that shortly. So, with that, I will try to give you a little geometric intuition about Fourier series. And this is very easy to do in discrete time, so we'll do it in discrete time first. I'm not even sure if I'll go into the continuous time, because that gets a little technical. So the title of this section, it's also in the notes, is that Fourier series is really a change of basis if you interpret it in a linear algebra or geometry way, the change of basis. So what do I mean by that? First of all, we are dealing with period and signals. So period could start at 0 and at n minus 1. So to fully describe a period and signal, I need to give you n numbers, x0 to xn minus 1, right? Once you know those numbers, the rest is just repetition of those numbers, right? So let's choose to represent this sequence as a vector. So I'll use this arrow notation for vector, which I don't like, but we need to distinguish it from x, which stands for the sequence, right? So the first entry I'm going to put x0, the second entry I'm going to put x1, and the last one is xn minus 1. So what's the dimension of this vector? N. It could be, if x is real value, it's an Rn, but we'll keep things general. Real is a special case of complex, so complex numbers c to the n, complex space, right? All right, so in the complex space c to the n, we also have an appropriate definition of an inner product of two vectors. If these were reals, what's the inner product of x and y? You just multiply the corresponding entries and add them up, right? If they are complex, you do the same thing, except that the second, or depending on the definition or the convention, it could have been the first. For me, it will be the second. You take the ith entry of the vector x, the ith entry of the vector
vector y and star that. Take the complex conjugate of that and add over I. But here, the entries of our vector are actually values of a signal, so I'm not going to write x sub I for the ith entry. The first entry is x of 0, so I'm going to put x of n instead. Our indices are not I, they are n. Okay, so x of n, y of n, star. And we go from 0 to n minus 1. All right? Any objections to this definition of the inner product? In the complex space, that's how we define an inner product. Okay? So scalar, what is it called? Scalar vector product, or inner product is, I guess, is not inner product. So you apply an inner product to two vectors, what comes out is a scalar. Okay? In this particular vector space, that scalar is a complex number. All right. So what? I just rewrote the sequence in vector form. What big deal, right? Well, the important thing is that those functions phi k that we've been using in our Fourier series expansion. Remember, phi k was e to the j k 2 pi by n times n. Remember that? Those I can also write as vectors. I can say phi k vector is phi k0, phi k1, because those are also periodic with period n, so I can also represent them as vectors. Why not? And you'll see in 1 minute or less why I'm doing this. Okay, so the entries are quite simple. Phi k0, no matter what k is equal to 1. Phi k1 is e to the j, k 2 pi over n. And the last one will be e to the j, k 2 pi over n times little n, in this case is n minus 1. Right? So a bunch of complex numbers form this vector. Okay? So the claim is that phi k from 0 to n minus 1. So if I take capital N of these vectors, they are actually an orthogonal basis for this complex space C to the n. Are an orthogonal basis for C to the n. So since our vector here since our signal was represented as an element in C to the n, that means I can expand, I can change my basis, and I can write my vector x as a linear combination of the new basis vectors, phi 0 to phi n minus 1. Okay, so following this claim is that I can take any x and I can write it as a0 phi 0, a1 phi 1 to a n minus 1 phi n minus 1 for appropriate coefficients a0 to a n minus 1. And that really is what we did in Fourier series, right? We just took any periodic signal, we decomposed it as a weighted sum of these functions phi 0 to phi n minus 1. The same thing can be written in vector form as a change of basis if you believe my claim that these phi k vectors are orthogonal to each other and they form a basis. All right? So this gives you a nice geometric view of things. So let me show this orthogonality property. Actually, I did show it to you. I didn't tell you this is orthogonality. One of you saw it and said, is this not orthogonality? Yes, it is, and you'll see why now. So take any k and m. So phi k, inner product phi m. What is that equal to? Our definition of inner product, just on the previous page, said sum over a period, we said 0 to n minus 1, doesn't matter as long as I'm summing is periodic, phi k of n times phi m of n star, right? That's our definition of inner product that we're using. But we saw earlier that phi m star is the same as phi negative m. Okay? We also saw that if I multiply two of these phi functions, it's the same as adding their indices. So that amounts to being phi k minus m n that I'm summing up. Okay? But then, about this sum, we saw something interesting. Remember those arrows pointing in opposite directions? They add up to 0. Unless we're talking about phi sub 0 or phi sub n, right? Unless k and m are the same, modulo n, this is going to give you 0, right? So the answer is 0 if k not equal to m. Let's just imagine that k and m both are elements of 0, 1, 2, and minus 1, so I don't have to keep track of modulo, etc., right? So then this sum here is 0 if k and m are different things. And what does that mean? They're orthogonal to each other, right? But if k and m are the same, what do I get? I added 1 n times, so that's going to give me n if k is equal to m. Okay? So what that says is that if I take n of those phi functions with different indices, they're all orthogonal to each other. And each one has length square root of n, because phi k, inner product with itself, means the magnitude of phi k squared, right? And I know that that number is equal to n. So phi k, so each of these vectors, these basis vectors, has the magnitude, the length of square root of n. Okay? If I want to be a little more, if I want things to look perfectly beautiful in a mathy way, if I'm a mathematic romantic, right, then I would not be satisfied with orthogonal. Orthogonal could have any length, right? Let's normalize everything to 1, right? So then I would have defined these basis vectors as 1 over square root of n times e to the j blah blah. I'm not going to do that, but the mathematician would have probably done that and told you the claim they're an orthonormal basis. And in the meantime, you've been wondering where the hell that 1 over square root of n came from, and only in the end you understand it was the result of a little bit of OCD to make everything like 1. But I'm not going to do that, although I have a little bit of OCD myself. So we're going to deal with this non-unit amplitude of the basis vectors. All right. So then things look nice. So I just write x as, again, do you believe me now? So the Fourier series is really a change of basis. If you look at the signal as a vector, it really is a way of writing. Instead of looking at the entries of x, which are the values in time, I'm instead switching my basis to phi 0 to phi 0 and minus 1. So I really now have to store the values of these a's, right? Instead of x0 to xn. But let's first see, how do I recover the coefficient k, given that these phi's are orthogonal to each other? Right? So what happens if look at this expression. If I want to find the mth one, let's say the second is A2, right? What's a good way of, given that these phi's are all orthogonal to each other, what's a nice way of cleaning out everything on the right-hand side except for the mth term? Take the inner product of the right-hand side with phi m, right? So take the inner product of this with phi sub m, and also with this, that means the whole thing here with phi sub m, right? What happens? Everything is eliminated because you're taking the inner product of orthogonal things, except for the mth term in the sum. And for that term, you're going to get a product of capital M, not 1 because it's orthogonal, not orthonormal. Okay, so what comes out is n times am, right? So this is equal to n times am. So am is simply 1 over n x by m inner product.
That is the analysis equation that we derived. Remember I told you multiply it with phi negative m, sum over blah, blah, blah. All of that is really doing this. If you take this expression, write it out explicitly using this definition of the inner product, you'll get the same expression as the analysis equation we had in terms of the summation, right? But this is much nicer looking, right? It's an inner product. So all you're doing here really is, because you have an orthogonal basis, when you view your signal as a vector, x, you're really projecting this onto the kth basis vector, right? How do you do projection? You take an inner product of x with phi k, and if it has unit amplitude phi k, that inner product will give you this length, right? In this case, we have to correct it by n, but really we are doing an inner product to project x onto phi sub k. So, and this is our analysis equation. Equation only prettier. Okay? So, oh, and that weird Parseval. What did Parseval tell us again? Parseval said x of n squared, when I add this over one period, is the same as, oh, if you divide it by n, unfortunately, it's the same as ak squared. And why is that? How do you interpret these terms on the left and right of the equation geometrically? Again, this 1 over n is really ruining everything, because if it was orthonormal, everything would have been simpler. But forget that for now. X of n entries squared sum for the vector x, what is that? It's the magnitude of the vector, right? Magnitude squared. What is ak squared? Well, ak, those coefficients a, if I form a vector from them, it's the same vector, right? I just changed the bases I'm representing in a different basis, right? So of course they have the same length. Why should it change? It's just a different representation of the same vector. That's basically what Parseval is saying. Okay, same length, because it's the same vector, it's just a change of basis. All right. So change of basis here simply means that instead of keeping track of the values in time, x0, x1, x1 to xn minus 1, instead worry about the coefficients a0, a1 to an minus 1. Okay? They are alternative representations of the same signal. When I use the original representation with the values of the signal, I'm putting the emphasis on time. I keep track. I store the values in time, right? So this is a time focused representation. When I ignore the time values but focus on the coefficients a, that's a frequency focused representation, because all I care about is how much of each frequency is present in this signal. What is the frequency content of the signal? So going back and forth between time and frequency is the main theme of this course, really. It's extremely helpful in terms of interpretation. It's also helpful in practice. For example, when you use things like JPEG or when you're streaming, what are the formats nowadays? I can't keep track of them anymore. They used to be MP3, but that's probably different. So now those things actually compress signals, right? The file size is not the same as, let's say you're sampling at 44.1 kilohertz. So you keep, that's how CDs used to be. 44.1 44,100 samples per second you take, right? If I store them, I'm going to take a huge file, right, with all the values of the signal at that time. Instead, what I can do is I can look at the Fourier expansion of that and try to store, instead of values in time, try to store the frequency coefficients. What's the advantage of that? Well, in time, every point is as important as any other point. Somebody's playing music, no time is different than other, right? But in frequency, they have different importance for your ability to hear them, right? So you don't hear every single frequency that, your ear has a certain bandwidth, right? So the main idea in some of these compression algorithms is that it will take the higher frequency coefficients, which don't matter that much to you because you can hardly hear them anyway, and maybe just toss them to save storage space, right? Or, since those numbers will have to be quantized anyway in digitizing the music, right, maybe use fewer bits to quantize them, so have a coarser representation of those coefficients, because, again, you won't hear them much anyway. But for the frequencies that you're very much attuned to, go full speed and use the full number of bits you want to reserve for that. Okay? So that's one of the many advantages of thinking in the frequency domain. You can compress your signal. Same thing in image processing. When you have JPEG images, they are not the same size as an image where every pixel is stored individually. Instead, you break it up into different frequency components, and we'll see an example of this in a couple of weeks. And then those frequencies that matter to you, those that move more smoothly, they are captured well with many bits reserved for those frequencies to store A sub k. But for some of the higher frequencies that you won't see or you won't distinguish, you don't care much about them. That's how we're able to compress images. Okay. So lots of interesting practical applications, as well as a beautiful, elegant way of thinking about signals. Now this covers discrete time. And those of you who took 16B, how many of you? Almost all of you, okay. You saw something called DFT, yes? You hated it, right? I know. So DFT means discrete Fourier transform. It is defined for finite duration discrete time signals, right? It is pretty much the same thing as what we just did. It's pretty much the same as the Fourier series of a discrete time signal. If I take my finite duration signal, whatever it looks like, maybe this, right? And splice it end to end, therefore creating a periodic signal, and find the Fourier series coefficient of that. It's up to a scaling factor which may or may not be there depending on which book you're looking at, up to a factor that's really the same as the discrete Fourier transform coefficients. Fourier series, discrete Fourier transform, they are pretty much the same thing. Okay? So when we taught you DFT, it came a little out of the blue, I know, but so we basically taught that as a change of basis to begin with. But you were like, well, what on earth happened again? Why complex? What's going on? So I know it was a little puzzling at that time. But really, this is what's going on. So this, hopefully, we're now coming full circle. And maybe you can look back at your notes from then and try to close the loop. Okay? If you have not seen 16B, if you have not seen DFT, do not worry. It's not essential. It was basically some variant of discrete Fourier series, and a similar interpretation of geometric interpretation of the Fourier decomposition as a change of basis. All right. So, what about in continuous time? Now, I'm not going to go into this very much, but something similar happened, right? So, in continuous time, we use the basis signals. Let me call it phi k again.
e to the j k 2 pi by t,
right? In continuous time, every k is a different k. All of these are different functions, and k goes from negative infinity to infinity. So we need an infinitely many number of basis functions in that case. Okay? So the problem in continuous time is that I can no longer represent my periodic signal as a vector in the usual Euclidean space, which is easy to visualize, right? 3D, 4D, whatever, right? So what I can do instead is, since these are periodic signals, I can just worry about what happens to the signal from 0 to t, because afterwards everything is a copy of the same thing, right? So then, each signal is a snippet of a periodic signal, one period of it, right? So then signals are basically things that look like this, right? And you can create infinitely many of those, correct? Unlike in discrete time where there are only so many degrees of freedom, right? There are only n instants there, right? Here it's a continuum. So it kind of makes sense that even if you can find a basis, it's going to take infinitely many of them, right? Because this is a continuum, right? The right way to do it, which we're not going to do, but I'm going to try to give you a glimpse, and by no means think that you fully learned it now, because there's, when you're dealing with function spaces like this, you have to be very careful, okay? So we can treat the family of such functions from time 0 to t as a vector space. Only now, each vector is not the usual, vector with the entries. Each vector is, in an abstract vector space, is a snippet of a function in time from 0 to t, right? So there is this so-called space of square integrable functions, okay? So vector space, and I'm not going to prove to you all the properties that are needed to make a space, a vector space, and all that stuff. So I'm just giving you some high-level ideas. So vector space of square integrable functions from 0 to t. So these are functions. Again, this is not going to be on the exam or anything like that. But, I'm just trying to tell you how the geometric view we had so nicely laid out in discrete time would carry over to continuous time if one wanted to do that, okay? And certainly this course is not enough to do it. You would have to take a course in function analysis or 110. Is that what's the math course that does all these abstract vectors? Huh? Or is it? But they do not do abstract vector space. Yeah, infinite dimensional. 110 is a good starting point if you want to learn how to do these things rigorously, not the way I do it. Okay. So these are signals x. So the objects here that we call, the moment I say it's not going to be exam, people are typing. So the objects here are not vectors in the usual Euclidean space, but they are functions mapping 0 to t to, let's say, complex numbers. Okay? Such that the family of all such functions whose integral from 0 to t exists and is finite form the vector space, and that space has a name. It's called L2. I'm not going to tell you what, well, I'll tell you. L for somebody called Lebesgue. 2 because the second power is integrable, okay? So it turns out, this is a space, okay? And in addition to satisfying properties you would want from a vector space, this space can also be endowed with a norm. So the norm of our signal, L2, so what we saw here, all these functions, they are basically a vector in this L2 space, right? And the norm of each one would be defined as the integral from 0 to t, x of t squared dt. By definition of this space, this is a finite thing, right? And I take the square root of that, and that defines a norm in this vector space. All right? In addition, in this vector space, I can go beyond just defining a norm. I can also define an inner product. I can take two signals, x, y, define an inner product in this form. 0 to t, x of t, y of t star, dt. Okay? And if you believe that definition of inner product, what do I get when I do the inner product of x with itself? X of t times x of t star. That is the same as x of t absolute value squared. So I really get the norm squared, which is what I would want to get, right? The inner product definition should match the definition of the norm like that. Okay? So, if you live in this very abstract space, then you can still interpret the Fourier series that is infinitely long as a change of basis. Okay? Because again, what we do is we take any arbitrary x and try to write it as a weighted sum of those phi k functions. So it turns out in this space, all those phi k functions are orthogonal to each other. Phi k t are orthogonal to each other. And that is a result of the following fact. If I take phi k, inner product with phi m, where k is different than m, the definition I just showed you above gives me e to the j k 2 pi by t, t, phi m star, that simply changes the sign here, m, 2 pi by t, t dt, all right? And that is the same as just combine k and m into k minus m, 2 pi by t, t. Look, this is just like what we were doing. Remember the vectors, those phi k's in discrete time, they gave us almost 0 always, except when the index was 0, because then you got all ones. Same thing is happening here, right? This is a sinusoidal thing. Over a period of 0 to t, I will have at least one cycle of this, perhaps more than one, depending on k minus m. So that will average to 0. That will give me 0, except when k is m. If k is m, that is just 1. So I'm integrating 1 from 0 to t, right? So the answer is t if k is m, 0 otherwise. That really shows that these phi functions are orthogonal in this space. Their inner product is 0 if k and m are different. Okay? In fact, now this really goes beyond whatever we can do in this course, but you can rigorously work maybe with 110 material or maybe a little more, that they form a basis as well. Okay? So then, just like what we did, you can interpret the Fourier series as a change of basis in this L2 space. Okay? This is how you would carry the analogy from the discrete time to continuous time if you were mathematically inclined. If you don't care, continue not caring, but I told you anyway. All right, so we'll continue next time. Oh, homework 1 is out today. If it's not, it will be soon. It's due next Thursday. This is not one of those Python labs. It is a homework, paper and pencil and all that, right? So you do it, scan, submit through GradeScope. Mark each problem where it is so we can grade.